Now presenting is Fiona Burnell from the University of Minnesota over topologically interacting, or topology and interacting and strongly interacting systems.
Okay, hey everyone. So yeah, I was charged with telling you a bit about the interplay between topology and strong interactions. And so in my first lecture, I'm gonna give kind of an overview of how this works, maybe with apologies to people who know the fractional quantum Hall effect really well. But I wanted to start at the beginning, and hopefully we'll get to maybe some slightly more advanced topics tomorrow. Okay, so we've heard a bunch. And actually, is this a pointer? Oh, this is the pointer. This is the very dim pointer. Okay. Yeah, so we've heard a bunch already from Joel about topology, a lot about topology in, thank you, in band systems. I guess what I'm going to tell you about today, okay, and right, so this is basically here, topology, when you hear the word topology, it's always some kind of winding, okay? And in band theory, we think of winding of specifically a Berry phase of a wave function around the Brillouin zone, okay? And obviously this is great. This is the right kind of topology to think about when you have a system where band theory is a good starting point, so a system where interactions are not too strong, and it's useful for a bunch of stuff, in particular, predicting robust, gapless edge modes, such as we see here. Okay, good. Now, the kind of topology I'm going to tell you about today is a different kind of topology. And here's my cartoon, which is meant to sort of pique your interest. But there's other kinds of winding that we can have, which are kind of specific to the case of strong interactions. And one such winding is, this is a picture showing two pairs of particles, a red pair of particles and a green pair of particles. And maybe they've appeared from the vacuum at some time. And in time, one of the red particles is going around one of the green particles and they're being reannihilated, right? And here we see another kind of winding, which is a linking of the world lines of these particles, okay? And what we're gonna hear about today is the story of anyons, which is basically in the presence of very strong interactions, this kind of linking can behave differently, and it tells us about a sort of different kind of topology, topological order in these systems. Okay. Now, more specifically, okay, it's very important to appreciate what would happen if I did this with a system of like any particle that you're able to isolate microscopically, which is going to be either a boson or a fermion, okay? So, we're used to, fermions, like there's this minus sign under exchange. Okay, if you look at what's happening to these particles, this is a double exchange, okay? So any kind of non-trivial, say phase factor or thing that's happening to my partition function in this process is telling me that there's some kind of statistics between my particles that are different from the statistics that I could have for bosons or fermions, okay? And that's where the word anyon comes from. Okay. So the story of anyons begins with the fractional quantum Hall effect. And, I think at this point, you've seen this picture a few times, right? So, we have this response where when we apply an electric field, the current flows perpendicular to the field. And the remarkable thing, the surprise about this effect was that this response is observed to be quantized, okay? And it can be quantized either in integers, okay, or in fractions. And so just kind of, again, as a warm-up for what I'm going to say, let me remind you about, what's kind of different about these fractions, okay? So this, I think Joel alluded to this argument yesterday, but you can ask, what are the low energy point-like excitations, or what are some of the low energy point-like excitations, quasi-particles, that I could make on a fractional plateau, okay? And one thing we can do is ask, well, what kind of excitations, could I make with a small deficit or excess of magnetic flux? Now, I just want to kind of remind you of a fact that you've probably seen in a quantum mechanics class, which is, what happens to like an electron, okay, if you put a solenoid or a tube of magnetic flux through the plane that the electron is moving in. And you will remember that when we add background gauge fields to quantum mechanics, we have to go from a momentum to a canonical momentum, okay? And the net result of this calculation is that if you look at the phase difference between an electron going around the solenoid on the right and an electron going around the solenoid on the left, there is a phase difference in that wave function. You can actually see it in interference in experiments, okay? And that phase difference depends on the flux enclosed by the solenoid, okay? Why am I reminding you of this? Because it's very important when we talk about this thought experiment, it's very important to be very clear on what kinds of flux, how much flux we are allowed to insert in our system to make something that is a quasi-particle instead of like a massive like defect, okay? That's like a whole kind of line, okay? And I guess I should tell you, so I'm just putting phi naught here, okay? So the point is that, there's this quantity phi, it's measured in units of, E over H, okay? And when phi, you'll notice that, like when phi is an integer in these units, okay, which is what we call a flux quantum, then the net phase between these two paths is an integer multiple of 2 pi, right? And the wave function is the same, okay? So when I poke my solenoid, my tube of magnetic flux, through my quantum Hall system, if I insert a fractional number of these flux quanta, right, what I'm actually doing, and I don't have a picture of this, but what I'm actually doing is creating a big branch cut in my plane, right, where the boundary condition of an electron going around this point changes, right? Okay, so that's not a point particle. That's some big defect, okay? That's not what we want. So the amount of flux that we're allowed to insert is an integer number of flux quanta. Let's do the minimal thing and insert 1, okay? Great. So here's the thought experiment. We insert our flux quantum. And obviously, yeah, so I taught like first year E&M last semester, so we all know, right, that this change, this time-dependent magnetic field as we insert our flux quantum creates an EMF, right? So an electric field going around this hole, right? But we have a Hall conductivity, right? So this EMF is going to, depending on the sign of the Hall conductivity, we're going to either suck a little bit of charge in, there's going to be a current flowing in, or maybe a current flowing out, okay? And you can calculate just from knowing the Hall conductance and nothing else, right? So from the empirical measurement, you can calculate how much charge builds up on this flux quantum as you poke it through your system. And you find that when you're sitting at an integer plateau, okay, that that in doing this, you pick up an integer charge on your flux quantum, okay? And when you do this on a fractional plateau, you pick up a fractional charge, okay? So this argument suggests that there should be point particles on this fractional quantum Hall plateau that carry a fraction of the electron charge, okay? Okay, so now let me remind you, so now we're going to think a little bit about these particles that have both flux and charge, okay? And now we can ask, remembering this Aharonov-Bohm phase that the charged particle feels when it goes around the flux tube, we can ask about these statistical interactions. So just to clarify, right, so what happens to my wave function when one of these particles goes around another, right? So this is a little animation showing in time the picture. This is equivalent to this picture of linked world lines that I had before, except the particles don't annihilate at the end, okay? And so what happens to my wave function when I do this? Under double exchange, I can see that just by, and there's some subtleties with factors of a half that I don't want to get into, okay? But under this double exchange, which would have to give me a +1 if the particle was a fermion or a boson, I get a phase of like e to the I pi over 3. Okay. Now, a fun thing about this phase, and we'll come back to this next time, is that you can convince yourself that this phase, what does it mean to be topological? Okay. When we talk about topology, we mean something that is completely insensitive to local deformations. Okay. And that is a fact about this phase. It does not care, right? It only cares about whether the one particle went around the other. It doesn't care about what trajectory it took, right? And fundamentally in the quantum Hall effect, this is because the system is gapped. Correlations are exponentially gapped. And so as long as I keep these two guys many correlation lengths apart, the only interaction between them is this statistical or topological interaction. Okay, great. So this is fractional statistics, right? Particles exhibiting fractional statistics are what we call anyons, right? And we can see that this kind of fractional statistics can happen in the fractional quantum Hall effect. And this is why the fractional quantum Hall effect is like qualitatively, I think from a theoretical point of view, so very different from the integer quantum Hall effect. All right. So today I want to, mostly sort of focus on some basic questions about fractional statistics, partly to kind of give some context to, I think, what Cecile is going to talk about a little later. Let's talk about what makes this happen, right? Like, so what do we need to find fractional? The fractional quantum Hall effect was a big surprise, actually, right? So ex post facto, we can come back and ask what kind of conditions do we need to be able to realize this rather striking physics. And then, the other thing that I'm going to talk about today is how do we describe this mathematically, right? How do we sort of understand what's going on? How do we write theories that will maybe allow us to understand the bigger picture, what kinds of fractional statistics or topological order can exist? Okay. And then next time I'll tell you maybe about more about this last question. Okay, so the first thing, we've heard a lot about moiré materials, and we've had a lot of people tell us about how much excitement there is about systems with flat bands. And so I just want to remind you that, what's special about the Landau level? One of the things that's special about a Landau level is it's very, very, very flat, and flatness allows interactions to be very, very important. So let me unpack this for you a little bit, right? So here's a particular choice of gauge for me to write the Hamiltonian for a Landau level, right? And in this gauge, it's convenient to express the wave functions as a function of x and plane waves in the y direction, okay? And when you do that, you see that the Hamiltonian for your Landau level basically looks like harmonic oscillators, right? With the slightly sort of different property that actually, this is like a harmonic oscillator that has a minimum for each of the allowed values of ky, okay? And that means that, so, suppose that the lowest energy thing I can do for a single particle in a harmonic oscillator, obviously, is put it in the ground state, right? So put it in one of these minima, but now there's a lot of minima, so there's a lot of places that I can put one electron into this lowest energy state of my harmonic oscillator, right? And you can ask, well, how many states are there for my electron? Right, okay, and so let's, to do that, to make that tractable, let's be concrete. Let's imagine that in my sample, I can actually make periodic boundary conditions. Usually you can't, but, this will give us the right answer. So we're going to do it as theorists. Okay, and so now my ky is quantized, right? And so the distance between these minima is also quantized, okay? And so now I can ask, how many of these minima can I fit into a sample with length Lx, right? And the answer is that the number of these states, gosh, is that my machine? Let me see. This is actually, I think, no, I think this alert is on the computer over here. Maybe I could do this. Okay, yeah, it's, okay, sorry. Okay, apologies, right. So the number of these states is just the total, number of magnetic flux quanta in my sample, okay? And so this is where this distinction between integer and half integer comes from. When we talk about the integer quantum Hall effect, what does integer filling mean? It means that the density of electrons is an integer multiple of the density of flux quanta in your sample, right? So a particular, density of electrons, we tune our magnetic field, and we get to this integer plateau. And the integer quantum Hall effect is great, but it is definitely not, at least if we're thinking about spinless electrons, a situation where interactions are very important. Why? Because I fill all of these states, right? And I have, like, if the magnetic field is high, I have this big gap, this big Landau gap to the next Landau level. Okay. However, when the density of electrons is some fraction of the density of fluxes, right, then, this band is totally flat. So this is like one of these situations, somebody gives you a Hamiltonian and you're like, great, I can solve the non-interacting problem, but now I add some perturbation, some interaction, right? And this is just a massively degenerate problem. And so to understand what this system is going to do, for example, to find its ground state, you really have to go back and diagonalize this problem in the interactions, right? If you think in terms of perturbation theory. In other words, the interactions are going to totally dominate the physics. And this is because we have this totally flat band and it's partially filled. So that's why flat bands are so important to thinking about finding exotic, phases with anyons. The second ingredient, so there's two things about the Landau level that are kind of special. And the second thing is that, if you think about a situation, and maybe I'll come back to my previous picture, right? If you think about a situation, the interactions are really strong, right? And, let's imagine this is like a 1D chain or something like that. And I have repulsive interactions between my electrons. And then you're like, well, actually, this is probably not going to do anything very complicated. The electrons are just going to localize, and they're going to kind of crystallize at some spacing. Okay. And so you also need, so flatness is not enough to, give you something with, for example, anyons in it, right? We also need some kind of way to prevent this localization. Now, I'm not going to maybe say too much about this, but this is where the topology, the non-vanishing Chern number of the lowest Landau level helps you, right? So there are systems you can write down models. This is from a recent paper. You can write down models with topologically trivial flat bands, Chern number 0, right? And in those cases, if you add interactions, there is not an obstruction to just, everybody localizing. And the lowest Landau level, it turns out that you can't, there have to be some states there that are delocalized, okay? This is not sufficient to guarantee you that your system will not crystallize. So if you take a Landau level at low enough filling with Coulomb interactions, you do get these kinds of electron crystals called Wigner crystals. But the non-trivial topology makes it, think of it as a way to make it a little harder for these electrons to just kind of crystallize and localize so that when you get to high enough densities, they have to do something else. Okay, great. So in other words, the two ingredients that are good for us are flatness and non-trivial band topology, specifically not, non-vanishing Chern number, okay, which helps us prevent crystallization. Okay. So where in nature should we look for this? Well, obviously now there is a great deal of excitement about looking at systems with flat bands, especially in 2D materials and wiry materials that have flat bands and non-trivial topology. And I think one of the things that we heard a bunch about yesterday and that Cecile will tell us more about is that actually there's a lot of systems now that can be made just in the last few years that satisfy this criterion, which gives us an extremely exciting, much larger phase space to look for this kind of exotic physics. And the other thing, which I won't say much about today, is the other context in which anyons have been discussed for a long time is in highly frustrated magnets, okay? And a magnet is kind of always interaction dominated. If you think about it, it always comes from a Mott insulator. Okay, but the frustration basically is there because in this case, you want to prevent magnetic order. And that is the context in which you get anyons. And in this context, these phases are called quantum spin liquids. Okay, great. So now I want to say a little bit about how we should describe anyons mathematically. Okay. And I hope that by the end of the lecture, you'll understand, why this is a useful exercise and not just a kind of some fun theory. But let me first go through the derivation. And I want to make a big caveat here, which is that, there's many different ways to derive the mathematical description that I will write down. All of them, I think, involve some rather ad hoc looking approximations, okay? And so you might feel a little bit uncomfortable with some of the things that I'm going to say. I hope to justify them, but I think it's very, very uncontroversial and also very mathematically clear that the final answer does give a correct description for the system. So bear with me. Okay. So the derivation that I'm going to tell you about today, which is one that is useful not only for studying fractional quantum Hall systems, but also for studying quantum spin liquids, is what we call a parton construction, okay? I'm going to tell you about specifically the parton construction today that is relevant to our quantum Hall plateau at 1/3 filling. There's many different kinds of parton constructions, depending on what kind of state you want, but hopefully this will illustrate the basic machinery that goes into this, which you can then use as a starting point to explore your favorite parton construction for your favorite state. Okay, so the basic idea of partons is let's build in to our description of the system this knowledge that ultimately we expect to see excitations that carry a fractional charge, okay? So I'm going to do that by describing my electron creation and annihilation operators in terms of a product of 3 things, and I'm going to choose a product of 3 fermions, okay? And these 3 fermions are all going to have a charge E/3. Okay. And the motivation for doing this is the idea is like F here, we expect if we get the low energy theory right, that F is going to be a creation operator for these quasi-particles that, that we argued from this basic flux threading argument should exist. And so it should describe, even though it's not I didn't put charge 1/3 particles into my sample, it's not a microscopic excitation, that it should be a good description of an emergent low energy excitation in our theory. Okay. Now, there's a problem with doing this, right? In fact, there's sort of 2 pretty troubling problems. I'll likely move this mouse here. Okay. There's 2 fairly troubling problems, okay? On the one hand, I have gone from a Hilbert space with like a single spinless, in my case, fermion per site, okay, to which has like 2, so imagine we're doing this on the lattice. Doesn't really matter, right? But it's just nice to be able to talk about a single site. And then I have a single site Hilbert space, right? And from my spinless fermion problem, there's only 2 states. I can have a fermion or not. But now I've introduced 3 fermions, so actually there's 8 states over here. So I've done something very, very naughty, which is that I've introduced a whole bunch of new states in my Hilbert space. At the same time, I've also made like a super redundant description of this electron operator because, because physically, microscopically, the theory has electrons. And you'll see that I can do these independent phase rotations of these 3 fermions, right? As long as the phases add up to 0, right? This is describing the same electron operator. So somehow there's a redundancy in my description of the physical particles when I break them up in this way. And in fact, in this particular parton construction, the redundancy is worse than this because if you actually look at, so these are fermions, right? So they're antisymmetric. So this operator here, F1, F2, F3, 3 different kinds of fermions, can be written in this way with an epsilon tensor, okay? And you may recognize that this is like the singlet representation of SU3. So actually there's like a kind of SU3 of rotation operations that I can do that will not change the nature of my actual physical operator that I'm trying to describe. Okay. But happily, these 2 problems kind of cancel each other out, okay? And they cancel each other out in the following way. So to deal with the fact that I have artificially expanded my Hilbert space, I'm just going to impose a constraint, okay? And so my constraint is going to be that, either I have a fermion or I don't, I cannot, and again, think about working on a lattice, thinking about, operators on a single site. I cannot create part of an electron. And so on each site or at each position in the continuum, the number of these three kinds of fermions is they're either all going to be 0 or all 1, right? And so now to impose this constraint, if I think about a path integral and I write down an action, I'm going to introduce some Lagrange multipliers, right, that would impose this constraint. And like I said, so here, here I'm writing down two of them, which is sufficient to impose this. But of course, there's a lot of other things that I could write down that would impose the same constraint. Okay, because of this SU3. And now the other thing is now, okay, so now basically what we've done is we've got these Lagrange multipliers, and I've suggestively written them as like A naught, okay? And then if you come back and you look at what's happening, in this redundancy here, you'll see that this kind of looks like a gauge transformation, like rotating the fermion by a phase, okay? And so the way out of this problem is I introduce these Lagrange multipliers, okay? And you'll notice that, yes, I can then think of this phase rotation in space as coming from gauge transformations that are due to coupling my F fermions to actual spatial gauge fields, okay? And when I do this, basically what I see is that, I've blown up the Hilbert space too much. I reduce it back down by imposing a constraint. Gauge theories always have a constraint, right? So you can think of this as like a Gauss's law. And then this redundancy in the description of the electron creation operator comes from the resulting gauge symmetry, right? And this is good because, this is always true of a gauge theory. A gauge theory, has the physical operators are the gauge invariant operators, right? So F by itself is not physical, and we expect this gauge redundancy. Okay, so this is great. So this is basically, I've done it specifically for this parton construction, but this is the general framework for any parton construction. We take our particle, we pretend that it's going to break up into multiple pieces, right? That has enlarged the Hilbert space and created this redundancy in the description of the physical operators. We solve that by introducing gauge fields, okay? So basically, if you want to work with partons, you are also agreeing to work with some kind of emergent gauge theory that's necessary for describing this system. So now let's come back to the fractional quantum Hall effect. And the next question that we would like to ask is, okay, I have my partons and they have to be coupled to this gauge field. That's not a choice. That came from my choice to use partons in the first place, okay? But now we'd like to know what is the rest of the action. And to find the rest of the action, the way that this game is played is we have to decide what state to put the partons in, okay? And for the fractional quantum Hall effect, we are going to assume, and I'll justify this in a sec, we're going to assume that our partons are just going to fill, each parton is going to like fill an effective Landau level. Okay. Now let me make a couple of comments about this. Okay. So you can think of this as kind of like a guess for what the partons should be doing. This is, always when I have partons, I have to guess that they're doing something, right? And basically, these guesses are only useful when we put the partons in a state that we know how to describe. In other words, a state that we can describe treating them as free fermions, right? So that's why I'm putting them in integer filled Landau levels, because now I know, how to write down the wave function. I know how to deal with them. I've turned my interacting problem into something that I can work with, okay? Now, this seems fishy. And often when it is used, it is a little bit fishy, but I think the correct way to think about this approach is that this is a way to just build a variational wave function, right? I take my partons, I put them into a wave function of my choice, in this case, filling Landau levels. I then project back onto the physical Hilbert space, and that will give me a wave function that is a valid wave function for the electrons, right? And then, often if you want to know, is that a good wave function, you can basically calculate its energy numerically and compare it to other states. Okay. And that statement is true, whether you're doing fractional and quantum Hall, where for other reasons maybe we don't need to do that, but particularly for quantum spin liquids, where it's often not so clear, you can try different parton wave functions. You can compare them to energetically to other variational wave functions and try to make your case for topological order in that way. Okay, so now let me come back to specifically the fractional quantum Hall effect. Why should our partons do this? Well, I'm going to give you two arguments. First of all, it actually gives you the right Hall conductivity, okay? So sigma xy is quantized in units of E squared over H, okay? And so here, I now have fermions where I've actually got, E over 3, so the charge is multiplied by a third, and there's 3 bands, right? And so I just add up the Hall conductivity of these 3 bands, and I indeed get 1/3 in units of E squared over H. Okay. Moreover, okay, I'm not going to talk a lot about wave functions today, but one thing that's not so hard to do, the Landau level is a non-interacting fermion problem, and you can write down, for the free fermions, the partons, you can write down the wave function in the lowest Landau level, right? And then you can project it, right, to say that, the number of partons of each type has to be the same at each location in space. And when you do that, the wave function that you get actually turns out to be the wave function that Laughlin guessed, okay, essentially, as a good ground state for the 1/3 state of the fractional quantum Hall effect. And more specifically, okay, it's not the exact ground state wave function for, gallium arsenide at the 1/3 plateau with Coulomb interactions. But it is the exact ground state for a Hamiltonian, which you can argue numerically is in the same phase as the nu equals 1/3 plateau. Okay. So in this case, specifically for quantum Hall, we have good reasons to believe that this parton construction is giving us a very good description of the wave function of the system somewhere in the same phase as this actual experimental plateau that we're interested in. Okay. So a few more comments. You might be like, well, okay, wait a minute. If you knew how to write down the ground state wave function already, right? And indeed, some of you maybe have seen this, like, you can take Laughlin's wave function, you can insert quasi-particles and quasi-walls. So maybe we already knew how to write down the wave function, not only for the ground states, but for these anionic excited states. So like, why are we doing this? And the answer is that some physical features, including fractional statistics, are a lot easier to compute from the gauge theory, and I'll show you this in a minute, than they are from the wave function. Okay? Yes? Yeah, good. So the question is, like, when I project back onto the physical Hilbert space, is that exact? So you can do it exactly, on a lattice. So if you put your particles on a lattice, right, you build your Slater determinant non-interacting fermion wave function out of F1, F2, F3, right? So this is why, more commonly you have to do this in spin liquids than in the quantum Hall case. But you build your Slater determinant wave function, and then basically numerically you can just go through and project onto the subspace of that Hilbert space where the number of particles on each, of each type on each site is commensurate with the constraint that you have to impose. Yeah. So and that's not to say that the ground state that the state that you're building with your partons is actually going to be the ground state of the system. That requires you to make a very well educated guess, but it will give you a valid wave function in that Hilbert space. Yeah, good question. Okay, yeah, and so and I think this the utility of thinking in this way will really, I think, come to the fore next time when we talk a bit more about, like, not just the 1/3 state, but all kinds of other states that we can understand in this way. And I hope to convince you that, going this rather bizarre route to obtain a theory with gauge fields is actually useful for understanding some of the physics. Okay, So, all right, so now we've chosen what to do with our partons, right? But of course, we had these gauge fields, and you might be disturbed by the fact that the original action that I wrote down, right, like there's like no gauge field kinetic term at all, because I just put them in by hand. And so we have to generate those gauge field kinetic terms, and they are generated basically by the back reaction of the fermions on the gauge fields. So if you like Feynman diagrams, you probably know what these mean, okay? But there's a calculation for the U1 case. It's not so hard to do. It's just this loop. There's a calculation that you can do which tells you that if you put fermions in this lowest Landau level and you calculate this back action, okay, what you generate for your gauge field is a term like this, which is indeed a Chern-Simons term. So I'm being a bit cheeky with the notation. I'm using capital D, which is a non-abelian gauge covariant derivative. But basically this should be the ADA plus 2/3 AAA that Joel wrote down. Okay. Now, some of you probably like calculating loop diagrams, so you should do this calculation because it will make you happy. If you don't like doing loop diagrams, you can sort of justify, at least in the abelian case, like why this should give you the right answer, okay? And the answer is if you take this Chern-Simons action, you say, okay, well, let's suppose that, I have a gauge theory and it's like, described by this Chern-Simons action coupled to the currents, right? And you can see very easily that this action, if I thought about it as an effective action for like an electromagnetic gauge field, it actually gives me, just from the equations of motion of this action, it gives me a Hall response, right? So it's very natural to say this Chern-Simons action should be something that comes about for gauge fields that are coupled to fermions that are like filling Landau levels. Okay. All right. So when we do this, and we had this like non-abelian gauge theory, okay, and we did this for the 3 bands of partons, and we get like a trace, okay, over these non-abelian, gauge field generators, matrices. And we get this theory here. And this has a name. It's called SU3 level 1 Chern-Simons theory. And the 1 refers to the fact that this number here is 1. It could not have been a half, but it could have been 2 or 3 or some other integer. Now, non-abelian Chern-Simons theory is a little bit difficult to work with, but in this particular case, okay, we don't have to work with it. We can work with a simpler theory using a deep fact about Chern-Simons theory is known as level rank dualities, okay? Now, there are some subtleties, for people who know this well, you will know that there are a few subtleties involving fermions, okay? But basically, the glib statement is all of the physics of the gauge field of an SU3 level 1 Chern-Simons theory is actually the same, in this theory with fermions as a U1 level 3 Chern-Simons theory. Okay. All right. And so for our purposes today, this just means I'm going to stop writing down the non-abelian action, and I'm going to talk about U1 Chern-Simons theory. Okay. And what does that mean? Okay, so now these are abelian gauge fields. They're again coupled to our, to our fermions. Okay, and now instead of having a number 1 here, I have to put a number 3 here. And we're going to study this theory. Okay, and we're going to ask ourselves, how do we describe the quasi-particle excitations of this theory? So our goal is to understand, where did this fractional statistics come from and how is it captured by this effective action? So here's like a picture of 2 particles, right? And maybe it's a particle whole pair, okay? So maybe I've acted with, one of my F daggers over here and an F over here. What is wrong with this? Tell me what's wrong with this operator. Okay. If these were electrons, this would be totally fine. Totally fine. But this operator is not gauge invariant, right? And that's because gauge invariance means I can do an independent phase rotation at R prime and an independent phase rotation at R, right? So net charge is 0. If it was a global symmetry, this would be totally fine. But for a gauge theory, this is actually not the right operator. And the right operator to make this gauge invariant is that I have to have a line, this is called a Wilson line, okay, an integral of the gauge field between these 2 points, and that's the physical operator. So now we have learned that if we want to describe things like the motion of our particles over time, right, what we're really talking about is, at any time I have like a particle here and a particle here, and they're connected by a Wilson line, by this line, okay, operator in the gauge theory. And so that means, it turns out that, when we think about this space-time picture, right, so these lines are important. That line is somehow, saying that there's a non-trivial operator in the gauge theory as I move this particle around in space-time. And now we can see that from our effective Chern-Simons theory description, this picture with the linked world lines of the particles now becomes concretely, when I want to calculate in the gauge theory, a picture with linked Wilson lines in this Chern-Simons theory. Okay. And so actually, you can calculate, if you want to know, okay, like what's happening with this braiding, one thing you can do, this is a space-time process, and I can just calculate the partition function of this space-time process, right? And let's call W1 the operator associated with this Wilson line, and W2 the operator associated with this Wilson line. And what we're doing is calculating the expectation value just of this like operator W1, W2. Now, this is a nice calculation. Remember, this abelian Chern-Simons theory is just quadratic in the gauge fields. Okay, so I didn't put the equations in, but you can look this up. This calculation can be done analytically. Okay, and what you find when you do this is that you get a number times what's called the linking number of the loops. Okay, and so this is how our Chern-Simons theory is capturing the statistics of the quasi-particles. Now, here's another perspective on a slightly different thing. So another thing that you may have heard about in the fractional quantum Hall effect is you might have heard about something like a topological ground state degeneracy. And so here's our world. We're going to live on the torus. Like there's a flat Earth society, and I think really we should start a toroidal Earth society. Okay, and so let's just look at, now let's talk about equal time. We want to think about ground states, okay? So no more space-time pictures. I just want to think about my theory as a function of time. And one of the things that this Chern-Simons action tells me, again, from the equations of motion, right, is here I'm on the torus, and I've told you I don't have charges, okay? I'm not going to have currents. And so therefore, the electric and magnetic fields, at every point on the torus are 0, okay? And in particular, that means that if I put a Wilson line, a contractible Wilson line anywhere on the torus, right, integral A dot dl around here, well, that's just telling, okay, here we go. Integral A dot dl around the United States, okay, that's telling us the total magnetic field of the United States. And so that's guaranteed to be 0. So like pretty much everything in our theory, just from the constraints due to the Chern-Simons action, is forced to be 0, but except for Wilson lines that run along these non-contractible curves, right? So I have like an integral of A dot dl around here. The red lines are a little bit faint, and an integral of A dot dl around here. And you should think of these not as measuring, magnetic or electric fields coming through the surface, okay, but as measuring magnetic flux that's like coming through this middle hole of the torus, or measuring magnetic flux that's going, through the center of the torus this way. All right. So now we can ask about these operators, okay? And one of the features of the operators that, again, you can pick off directly from this action is if I look at the part of the action that involves time derivatives, which is where I get the canonical commutation relations for my fields from, right? I can see that I have like an AY DTAX and an AX DTAY, right? Okay, and then I integrate by parts and these two combine. And this tells me that the commutator between AY and AX, right, when they're at the same position, has this factor of 2 pi I over 3. Okay. And now if I look at these Wilson lines around this non-contractible curve and this non-contractible curve, right, they intersect at one point. And so that actually tells me also that these two Wilson lines around the different non-contractible curves fail to commute. Okay. And moreover, right, these are just closed line operators. They're not creating any particles. Okay. So these are operators that must act on the space of ground states. I haven't like poked any holes in the earth. Okay, haven't made any excitations. And so the implication of that is that this theory has a ground state degeneracy. You can see that very easily, right? So let's suppose that I have a ground state, right? And if the ground state were unique, it would have to be, oh, I'm sorry. You know what? I've sort of I meant to act with the exponential of this operator. Okay, so but because I've put the phase in the exponential up here, but the argument is the same. Okay, so this is an eigenstate of one of the Wilson lines, right, with some eigenvalue. And now I look at a different state where I act with the other Wilson line on this ground state, right? And like I said, I should have written e to the I integral AX dx, e to the I integral AY dy. Sorry about that. But basically what you see is that this state here is an eigenstate, is also an eigenstate of this operator here, okay? But it has a different eigenvalue, right? So that basically tells us that we have, an operator that keeps us in the ground state space, but changes the eigenvalue of this Wilson line. And therefore, there must be multiple ground states. Okay. And in this case, you can show that these commutation relations force you to have 3 ground states on the torus. Okay, great. So in this way, we started with partons, we derived this effective gauge theory, and we see that it's very useful if we want to understand the fractional statistics and also this topological ground state degeneracy of our theory. Now, you might ask, okay, that was kind of crazy, right? I said, I imagine my electron broke up into 3 pieces, right? And then like magically, just by imagining that, I got this theory that actually had these crazy fractional statistics and fractional charges. And we know from real experience that this is not a common thing, okay? And so let me tell you a little bit about what's special to the fractional quantum Hall effect that makes this fractionalization kind of mathematically easier there. So many of you, if you've sort of taken a course in quantum field theory, maybe you've seen this famous, calculation for QCD of what's called asymptotic freedom, okay? Asymptotic freedom is actually the statement that a non-abelian gauge theory, unless it's coupled to a lot of fermions, typically in the infrared, so at low energies, becomes confining. This is what we see for quantum chromodynamics at the energies that we live at, right? We don't see quarks, we only see protons. Okay. And this is actually also true of U1 gauge theories, provided that it's U1, so lives on a circle rather than living on the line, that there's a famous argument by Polyakov, the calculation is different, that shows that these are also confining. And so usually if you play this game, right, and you say, hey, I'm going to fractionalize my electron, and then I have these gauge fields, but usually if you play this game, what's going to happen is once you calculate this effective gauge theory action, you're going to get like, an F squared term, right, an E squared plus B squared term. And typically that is going to lead to a theory where actually at low energies, your theory is going to tell you, these partons were not free, they were confined. And so really you're going to get back to a theory where your low energy excitation is the electron. So one of the things that's sort of special about the fractional quantum Hall effect is that once we generate this Chern-Simons term, it actually prevents this confinement, essentially from the statistics. There's a nice paper by Eduardo Fradkin that shows this for the U1 case. But it's true in general, okay? And so, this tells us that once we have these Landau levels, once we have this Hall conductivity, charge, the partons can be freed and charge fractionalization can happen more easily. All right. So basically, the moral of the story is we took this actually really complicated problem, right? If you try and sit down numerically and do numerics and diagonalize some interaction in the lowest Landau level, like that's a very hard problem. And we turned it into a much, much, much simpler problem about, this like quadratic abelian gauge theory. This gauge theory is useful because it captures the topological features of the fractional quantum Hall effect, namely the fractional statistics and the ground state degeneracies, right? And I guess I want to say, for the 1/3 state, we could have done this with the wave function, but now by understanding this description, we kind of have a handle on a more general picture that we can use to start to ask what other kinds of maybe more complicated states might exist. And yeah, that is indeed, So that is indeed where I plan to stop for today, which is perfect. We have maybe a few minutes for questions.
I think we can do. I think we can do about 2-ish questions. So anyone?
So yeah, nice talk. Thank you. I just had one question on the second to last slide. You talk about how like Landau levels, it's sort of natural for particles to fractionalize, and that doesn't necessarily happen in other cases. Do you have some intuitive understanding of what's like special about a Landau level that promotes the ability for particles to fractionalize?
Yeah, so I think there's sort of two perspectives on it, right? One is like, we talk about partons, and then, again, there's kind of this very heuristic, a Chern-Simons term describes a Hall response, right? And so, also whatever that interaction between the fermions and the gauge field is, it's very natural to say it's going to generate a Chern-Simons term. And so the technical answer to that question is the Chern-Simons terms, once you add those to your gauge action, they basically prevent this confining transition from happening. Now, there's also a physical picture, and that maybe comes back more to this business of like flatness and obstruction to localization, that we know that whatever is happening, it is 100% determined by interactions, right? Laughlin kind of guessed a wave function by saying, okay, Coulomb repulsion is going to make the electrons want to be as far apart as they can, okay? And this gives you, a Laughlin wave function, Zi minus Zj cubed. So I guess those are the two kind of handles that I have on how to think about that, if that helps.
Yeah, thank you.
I loved your talk. Thank you. I want to ask if you divide this in like the 3-parton thing, does it happen for other plateaus of like fractional quantum Hall? And if yes, then what do you do for like even denominator plateaus? Yeah.
Yeah, okay, perfect. Yeah. So there's a lot of freedom in these parton descriptions. And so we can go back, maybe I can go back to. Yeah, here we go. Okay. So basically, if you wanted to describe another plateau, right, you can still use a parton description, but you would use a different parton description, right? So if you wanted to go to, say, 1/5, right, you might tell yourself, oh, well, now I expect, excitations with charge 1/5. And so then you could write down 5 fermions. Now, if you want to go to 1/2, right, you'd be like, oh, there's excitations with charge 1/2. Maybe I should write down 2 fermions, okay? But that's not quite right, because 2 fermions will give me a boson. And so then I have to do, 1 fermion and 1 boson would be an option. And so yes, the description is much more general, but the construction would be state specific. Yeah.
Awesome. I think that we can now do the